All right, so one solution, most common option. Infinitely many solutions means there's too many to count. We can't narrow it down to just one. There's an infinite number of possible solutions for that. And then the third option is that there's no solution. So no matter what method we decide to use to solve a system, no matter what size the system is, these are the three options. There's one solution, infinitely many solutions, or no solutions. This is when we're dealing with linear equations. When we get to nonlinear systems, this doesn't hold true. Okay, so this is linear systems, and I'll tell you what section that the nonlinear is in, and they're easy to recognize. Okay, so if we're dealing with linear systems, I'm just going to briefly sketch what it looks like is happening. On a coordinate plane, if you're dealing with a linear system and you graph two lines, that is an image of what one solution is going to look like. Because these two lines cross in how many places? One. Okay, so that's what one solution looks like if you graphed it. When you're dealing in 3D, like three variable systems, and we'll get to that in just a little bit, it's a little tougher to draw, not really easy for me to draw anyway, but it's like three planes coming together. And the best way I can describe it maybe would be like the corner of the room. If y'all look back there in the back corner, where the ceiling, the orange wall, and the gray wall meet is one spot, one point. That's what one solution looks like with three variables. It's three planes coming together to one point and makes that corner. So that's kind of give you a visual for that. If you're looking at, that's one solution. Coordinate plane for infinitely many solutions. You got one line drawn. The other line lies right on top of it. How many places is the red line touching the blue line? Lots. Too many to count. So that's an infinitely many solutions picture there. When you're dealing with 3D, and infinitely many solutions can look like two planes right on top of each other. It could look like two planes meeting at a line. So if you think about where the ceiling meets the wall, that's a straight line. There's a bunch of points there. So it's an infinite number of them. So that's kind of give you a visual for that. And if there's no solution, what do the two lines you think do? They don't cross at all. And if two lines never cross, what are they called? Parallel. That's kind of the idea there, is that there's parallel lines. If we're talking about in 3D, we're talking about maybe this wall over here and that wall back there, never going to cross. So there are no solutions to that. So there's a visual of what one solution, infinitely many solutions. So one, infinitely many, and no solutions. None. That would be a visual of what those look like. Okay.
So the second one is always going to be when you have two lines laying on top of each other.
Yeah, infinitely many solutions is two lines laying on top of each other. That's what the picture looks like. Now, we're not going to draw the picture very much. We're not going to graph to solve, because that's not a good way to solve. It's if you're off just a little bit with one of your lines when you graph it, then you're off a whole lot. It's kind of like, I don't know if anybody shoots guns or anything in here, but if you're shooting a gun and at 10 yards you're off by a half an inch, at 100 yards, how much further are you off? You're off, a whole lot. So that's the idea, that the reason that graphing is not a good option. Having the idea of what the picture looks like is a good idea. That's the visual I want you to see, is that we get one ordered pair when there's one solution, a ton of ordered pairs when there's infinitely many solutions, and then no ordered pairs when there's no solution. That's what I want you to get out of that. We're not going to graph to solve. That's not a good method as far as graphing linear systems goes. All right, so I'm going to show you a couple of systems here, a couple of different ways to solve it. The first way is called substitution. And I'm going to show you this because we need this skill to do nonlinear But this is not the way that you're probably going to solve systems of equations the rest of the night. Linear systems. You're going to use the calculator most likely. So I'm going to show you this because we need to know what I'm saying when I bring this up with nonlinear. So here's our first equation: 2x minus y equals 2, and then y equals negative x minus 2. Those are our two equations. Substitution means you're going to substitute one thing for another. So you have one equation that has x and y in it, and they're on the same side. The second equation has y by itself, and it says that y is equal to this. So that means you can substitute that in for y in the other equation. That's what the substitution method is asking you to do. So you end up with an equation that has just x's in it. So we replace y here with this stuff right there. So that creates an equation that only has x's in it, which is one we can solve. When it's got two variables, you can't solve it. You can graph it, but it doesn't help you as far as solving it goes. So we can solve this one. Ends up being 2x plus 2 equals 2. So that's 3x plus 2 equals 2. Subtract 2. Get 3x is equal to 0. Divide by 3. X is 0. We have x to get the y value that goes with it. We can plug that back into one of these other equations and get y. I'm going to go back to this one because that's pretty easy, because it says y equals something. All I got to do is plug in the x that I know. So that'd be y equals negative 2. So the ordered pair is 0, negative 2. That's an example of substitution. Again, not something I'm expecting you to do. Even I'll explain it when I hand out the labs. It's going to say use substitution, but I'm not expecting you to actually do it with substitution. I want to show you how to use the calculator to help you. That's going to speed things up so much and eliminate a lot of errors with that. So that's substitution. Let's look at another method. It's called elimination, and this one is my favorite. If I have to do them by hand, I'd rather do them by elimination than substitution, just because I like it better. Not necessarily that it's that it works better. It just, I like it better. I don't know why. Maybe it's the one I was best at when I was a kid. That's probably what it is. So here's our system of equations. We got two equations. We got 3x minus 4y equals 1, and then the second equation has negative 3x plus 6y equals 7. So you got two equations. They both have x and y in it, and neither of them say x equals this or y equals something. They're both set up the same way. What we can do with elimination, the idea is that you just add the two equations together, because if I add 3x plus negative 3x, what happens? They cancel each other out. They eliminate one another. And then negative 4 plus 6 would be positive 2y. 7 plus 1 is 8. And now I get a really, really easy problem to solve. Divide by 2, and y is equal to 4. And then I take that answer and plug it back into one of those others to get x. So I'm gonna go back into the first one. That's 3x minus 8 or minus 16, excuse me, equals 1. And I would add 16. 3x equals 17. Divide by 3. X is 17 over 3. And it's okay. It's a fraction. That's not a deal breaker. In fact, that's more realistic than the problems there you don't get fractions. Systems of equations are really, much larger systems, definitely helpful in guidance systems. I don't know if anybody went to see Hidden Figures, that movie, but that just came out. It's a really good movie. Not just because it's math, but it's just had a good storyline to it. But anyway, they use systems of equations there when they solve huge systems of equations with all these variables based on the wind and the weather, barometric pressure, and all those. There's too many variables to do it just as one little equation. It's a system of equations of all the scenarios that could happen, And by solving that system, they get the one solution to how to launch that rocket and get out of the atmosphere in the right way without blowing it up. So systems of equations is much larger than this, obviously, and much more complicated. More complicated in the fact that there's a reason that they needed that big computer to help them because the systems were just so large. But elimination definitely a good other option as far as that goes. But the option that I want to show you is using the graphing calculator to help you, and that's using an augmented matrix. An augmented matrix, and let's just take let's see, let's do this set of equations. Example C: 3x minus 4y equals 1, and then 2x plus 3y equals 12. Okay, so with the matrix idea, what we're doing is we're creating this matrix and we take the variables out of it. That's another great thing that happens with the matrix is the variables go away and you don't think about them. Okay, the x's and y's sometimes messes up in math. So I'm just writing this down and I'm going to explain what it is. This matrix is a 2 by 3, meaning it has 2 rows and 3 columns. 2 rows and 3 columns. And the first column are the x's. The second column are the y's. And the third column is what it's equal to. And 1 and 12. Okay? That's what's called, it's called an augmented matrix because it has the what it's equal to on the side. If it's a coefficient matrix, if you see that word somewhere, if you're reading through the book trying to find another example, it says the coefficient matrix, then it's just talking about the numbers that were in front of the variables. That's the coefficient matrix. An augmented matrix is what we're going to use. Okay, and we set that up that size, 2 by 3, 2 variables. There's 3 columns. That's how you're going to know what size to do. And we'll go to a bigger size in just a little bit to do the larger systems. Now I want to show you how to use your calculator to help you. There's this skill or this function on there called RREF. It stands for Reduced Row Echelon Form. It doesn't matter if you know that or not. RREF is what you need to know. Okay. So what we're going to do with the calculator is we're going to go to the matrix menu. The matrix menu is you hit second, and then down here on the left, up here in blue, it says matrix, and it's the X to the -1 button. Okay. I don't have anything in mine. I cleared all my stuff out. If you've got something in there, that's okay. We're going to take care of it in a second. All right. The first menu that comes up is the names. That's the one you're going to use it later. We'll get to that in a minute. The second menu, if you press the right arrow key, is the math menu. We'll use that in a minute too. That's when it's actually doing some work. We want to go over to edit because we need to enter in a matrix. We need to edit one. So I'm going to hit enter on matrix A. And it comes up here, and it should start up here beside where it says matrix A. It's going to ask you what size do you want. If you already have one in there, just type in the size we need. We need a 2 by 3. So I'm putting 2, enter, and then 3, enter. And it makes the matrix that size. And it's set up the way that we've got ours done in the problem, right? We've got 3 columns, 2 rows, or 2 rows and 3 columns. So the first row should be the first equation, which was 3, -4, and 1. The second row are the numbers from our augmented matrix, 2, 3, and 12. And then just make sure you got everything in the right spot. Because if you have one thing in the wrong spot, it's like calling the wrong phone number. You ain't going to get the right person. Okay. So we've got our matrix in there. We're going to press second mode to go back to the regular calculator screen. And then I want to go back to the matrix menu because I want to pull up one of those math functions. So second, X inverse, which is right below the math button. And then I want to go to math. And the quickest way to get there is press the up arrow key. You can press down a whole bunch and get there, but I press the up arrow key because it's just a few less clicks. And RREF is what you're looking for. It should be alpha B, or you can just press the up arrow key is what I do. Okay. RREF. Everybody found that? All right, hitting enter. Now it put that on the regular calculator screen. That's why we went back there, okay? Because it's going to do the math here. Now I need to pick out what I want it to do the RREF to. I want it to do the matrix A. So I got to go back to matrix. And then this is where I'm using it from the names menu. I'm picking matrix A. That's the one I entered. And my OCD makes me click the parentheses. You don't have to. It'll do it anyway. But I always just do it just because I can't stand to not finish it. And then hit enter. And what that creates, it does these row operations, and we'll talk about those later on some just not systems of equations things. And it works with this thing until it gets a problem worked out to where you get 1, 0, and then it was 3, and then 0, 1, 2. What that tells me is that x equals 3 and y equals 2. The first row is x's equal. The second row says y equals. If it's a three variable system, first row's x, second row's y, third row's z, and then going from there. It's always in alphabetical order. X, Y, and Z. So the first row says x, no y's equals 3. Second row says no x's, but 1 y equals 2. Because remember, the first column's x's, second column's y, third column's the answers. So that gets us this ordered pair, 3, 2, is the solution to that system of equations. Now, that same system could have been solved with substitution or elimination and would have gotten the exact same answer, but much more work involved. Okay, this is how I'm expecting you to solve systems of equations. I don't expect you to do the substitution elimination for us. I mean, unless you're planning on going on to calculus or something like that, I don't see that being a need that you have as far as I'm concerned, as far as this goes. And honestly, I don't believe I remember solving any systems of equations in calculus. It's been a few years since I took calculus, but I'm pretty sure I didn't do systems of equations in there either. The only other class I did systems of equations was linear algebra, which was math 310. And I don't think anybody here is going to be required to take math 310 because that's a math majors and engineers course.
So, example A, like y equals negative x minus 2.
Mm-hmm.
With x and y, would x be negative 1 and y be 1?
You would need to move the x over to the other side. We're going to see that as we do some examples here, how we need to make sure our systems are set up the right way before we put them in the matrix. If they're not set up the right way where x and y are on the same side, then it's not going to work. We've got to get them set up right. So we're going to see that as we go here. All right, so let's look at another system. Kind of address Darren's concern here. Let's say we had 3x minus 2y equals 4, and maybe we had 4y is equal to negative 5x plus 8. So with this one, it's not set up correctly because the x's and the y's aren't where we can have columns of x's, columns of y's, columns of plain numbers. So we would need to move this 5x over here so that becomes 5x plus 4y equals 8. You need to do systems of equations, especially with the augmented matrix. You need the problems to be in that order. So you'd have 3, negative 2, 4, 5, 4, 8. And again, we're going to do RREF on that matrix. And so I'll click back over there so you guys can still see that. So we're going over to calculator. We're going to hit second matrix. We're going to edit, and I'm just going to edit matrix A. It's a 2 by 3 again, and then I'm putting in that system. We got 3, -2, 4, and then 5, 4, 8. And here's the good thing about reusing matrix A. Instead of having to press all those keys to get RREF, you just press the up arrow and go grab that where it says RREF of A. And it doesn't remember what the other matrix A was. It's a new one now. It's going to say, okay, I'm using matrix A, whatever's in there that you put. And it gets these decimal answers. And you know I don't do decimal answers, right? So how do we change it from decimals to fractions in the calculator? Math 1, or enter, and then hit enter again. And they'll change it over to a fraction for you in the matrix form. So that tells us that what's x in this problem? And y is, yeah. So the ordered pair, 16 over 11, 2 over 11. And most of the time you're going to see answers in an ordered pair or ordered triple form when we get to 3 variable systems. Always going to be looking that way. Okay. All right. Let's look at this. 8x minus 2y equals -4. And -4x plus y equals 2. Let's look at this system. Solving it with a matrix. Is it in the right setup? Is it ready to put in a matrix? You have a column of x's, column of y's, column of numbers. 8, -2, -4, -4, 1, 2. If one of the variables is missing in your equation, then just put a 0 in its place. Like if it didn't have an x, put a 0. If it didn't have a y, put a 0 in its place. That's what we're doing. Again, we got a 2 by 3 that we're dealing with here. Nothing changing as far as that goes. And let's run RREF on that system. So second matrix. We'll edit matrix A again. 8, -2, -4, -4, 1, +2. And then I'm going to go grab RREF again. And then look at what it gets me. Oh, man, that's weird. It doesn't have the 1s and 0s in the same place. Look at that bottom row, though. That bottom row, so you got 1, -1/4, -1/2. And the bottom row is zeros all the way across. What does the bottom row say? It says that 0 x's plus 0 y's is equal to 0. Is that true? Does 0 always equal 0? Yeah, 0 is always equal to itself. So what this tells us, by having all zeros all the way across on the bottom row, that bottom row right there tells us that this thing has infinitely many solutions. Infinitely many solutions. That's what all zeros in the bottom row tells us. That's what we need to know. Doesn't really matter what's up there in the first row. That would be the answer. That's where we're going to stop. We're not going to go into what form they would be in and all this stuff. There's some more you can do there, but it's not something that we need to really dive into, because it gets pretty robust after when you start diving into that part. So we just want to recognize that this has infinitely many solutions. All the ones we've done previous to this had how many solutions? One ordered pair solution, because there was one answer out of that, one ordered pair out of that. So this one has infinitely many. Let's look at this system. 3x minus 2y equals 4. Negative 6x plus 4y equals 7. Into that matrix, into your calculator. And see what's going on with it. Second matrix. Edit. And when you run RREF, you may see something a little different at the end. I don't know what you mean by missing a 0. I don't think it's missing a 0. It has an extra 0. Maybe that's the better way of saying it. Because when you do RREF on that, so this is what you got. Is that what you got? Yeah, math, or excuse me, go to matrix, go to math, and then RREF, and then you got to pick the matrix you want. I just arrow up to where I've used that before and grab it from there. That's the easiest thing. That's the quicker way to do it. So look at the bottom row. What's the bottom row have? It has 0, 0, 1. It says 0 times x plus 0 times y is equal to 1. So that'd be 0 plus 0. What's 0 plus 0? Does 0 ever equal 1? Mm-mm. So that would be no solution, because that bottom row. Okay, so we get 1, negative 2/3, 0, and 0, 0, 1. That bottom row, again, tells us that there's no solution. 0, 0, anything. Doesn't necessarily have to be a 1 in the last spot, but 0, 0, and then a number, that's no solution. That's it. That's it. Exactly right. Anytime it's all zeros all the way across in the bottom, it's infinitely many. All zeros and a number at the end, no solution. Won't always be a 1 there. Sometimes it's a different number, but a lot of times it is a 1, but not always. Yeah. All right, so we've done 2 variable systems. We've seen all the scenarios for an XY system that has X and Y variables. Let's look at a larger one that's got 3 variables. Okay. G. Let's say we had X minus Y plus 5Z equals negative 6. 3X plus 3Y minus Z equals 10. And X plus 3Y plus 2Z equals 5. Now, if you were going to do this by hand, it would take at least 1 piece of paper, because it takes a while. What you end up having to do is actually do elimination with 2 of the equations and get rid of 1 variable, and then take another pair, like maybe do 1 and 2, get rid of x's, and then do 2 and 3 and get rid of x's, and then you have a problem that's only got y, 2 problems that have y and z in it, and you've got to solve that system to get 1 variable left, and then you got to go backwards and get all 3 variables out of that. Tons of operations, tons of places to make mistakes. I'm not asking you to do that. I'm asking you to just say, okay, look at this system of equations, and let's think about what's the augmented matrix for this. What size should this augmented matrix be? How many columns? 4 columns, 3 3 lines, so it's 3 by 4. 1, -1, 5, -6, 3, 3, -1, 10, 1, 3, 2, 5. So a 3 by 4 system for this one. 3 by 4 augmented matrix. And we're still going to do the same operation. We're going to do the RREF action on this thing. What I normally do is when I'm setting up to do, I know I'm going to do system of equations, I'll use matrix A as my 2 by 3, and then matrix B will be my 3 by 4. Well, not 34, but hey, just go in over the top of it, like overwrite. Like if there's already a matrix in B, just go ahead and go into B and change it to a 3 by 4 size. Oh, okay. And then you can type over the top of any of them that are in there. It'll just type over the top. So 1, -1, 5, -6, 3, 3, -1, 10, 1, 3, 2, 5. All right. Again, second and quit. And then I'm gonna hit matrix, and I'm gonna grab that RREF under the math menu. This time I'm not gonna go up there and grab one I've already used. And then I tell it I want to use matrix B. And crank it out and look at the first row, 1, some zeros, and then a number. So that tells us X equals 1. Second row, a 0 for X's, 1 Y, no Z's equals 2. Third row, 0 X's, 0 Y's, 1 Z is equal to -1. So we get X, Y, and Z out of that. 1, 0, 0. 1, 0, 1, 0, negative, or not -2, but 2. And then 0, 0, 1, -1. That tells us that X equals 1, Y equals 2, Z equals -1. It'll always be in that order, top to bottom, X, Y, Z. So you don't have to really think about that too much. Ordered triple is how you write that. And in alphabetical order, X, Y, Z. And get that 3 variable system going. All right. Nothing changes as far as if it's no solution. The bottom row is still going to be zeros and then a number. If it's infinitely many solutions, the bottom row is going to be what? All zeros. Everybody's a 0 on the bottom row. So that's how the 3 variable systems doesn't change any of the rules. It's just a bigger matrix to put in. It's the only thing that changes that. Okay, so infinite many solutions, zeros all the way across the bottom. No solutions, zeros, and then a number on the right. That's all you got to remember, really. So that's solving systems of equations using matrices is the way that I'm really asking you to do it throughout the whole chapter with linear systems. All right, so that's section 5.1 and 5.2. And then let's go to section 5.3. All right, there's this thing, matrix, or matrices is the plural for matrix. Determinants, it's like a property of them. It's a number that they have. It's kind of like the property of that wall's orange. Doesn't really mean anything other than it's just that's what's going on. That this has a determinant, and it happens to be the number 5 or something like that. So when we're looking at determinants, it's like a property of the matrix. And you know, the matrix is just a number. When we're doing determinants only exist for square matrices. And by square, I mean like 2 by 2, 3 by 3, 4 by 4, that sort of size, n by n. The same number of rows, same number of columns. This is completely separate for the moment between this and solving systems. This is just something we need to be able to find. It's one of the pillars of this class for some reason. Okay. The determinant is only going to exist for square matrices. So if they ask you to find the determinant of a 3 by 4, it doesn't exist. Cannot do it. No solution to that. All right. So let's start with the easy ones, and that's the smallest ones. A 2 by 2 matrix. And it's just got numbers in it. I'll call them A, B, C, and D. I usually don't use the calculator to do this one, to do a small one like this, because it takes me too long to type it in. I can do the math quicker. Because the way it works is you multiply the diagonals there. A times D, and then you subtract B times C. That's the formula for finding the determinant of a 2 by 2. Okay. Example A is 2, -3, 5, 7. And here's how they can tell you to find the determinant by putting the matrix in what looks like absolute value marks. The absolute value marks means determinant. Square brackets means this is a determinant. They could write DET and then the matrix, and that means find the determinant, or they could put it in these absolute value looking bars. That means the same thing. So the notation there, you just got to know what it means. If it's in absolute value bars, that means determinant of that thing. Okay. If it says DET and then the matrix, that means determinant of that thing. Those two things mean the same thing. I don't know why they use both of them. This book tends to just bounce back and forth all over the place with that notation. Okay. All right. So I would just do this. I'd do 2 times 7 minus -3 times 5. That's how I would do this. I'm going to show you how to do it with the calculator, but and the determinant of that matrix is 29. What does that mean? Not much, which means it's 29. The biggest thing with the determinants is the fact that they're not 0. If they are 0, then there's something special happening, and that relates to solving a system of equations, but we're not going to solve systems with zeros with determinants anyway. So that's something for, like I said, that Math 310 class is really where that comes in. Now, with the calculator to do a determinant, I'm going to show you how to do that. You just go to your matrix, go over to edit, and put you a 2 by 2 in there. So I'm just going to use matrix A. I'm going to change it to a 2 by 2 matrix. And I'm going to type that one in. 2, -3, 5, and 7. And then I'm going back to the regular calculator screen. So second mode to go back to the regular calculator screen. I'm clearing all that out so I can get back to the top. Now, I want to do the determinant. That's a math thing with matrices. So I'm going to hit second, matrix, go over to math, and the very first option is DET. That's determinant. So I'm going to hit enter on that. And then I'm going to tell it to what to take the determinant of. And I put mine in matrix A. I don't know where you put yours, but I used matrix A. Hit enter, and it cranks out the number. Doesn't show you any of the math that works. It just gets you the number. By the time I typed all that stuff in and went back and got DET and all that stuff, I could do it by hand on a 2 by 2. Anything bigger than that, it's not faster to do it by hand. I used to be really fast at doing them by hand. I'm not as fast as I once was. I don't. There's not much need in doing them by hand, honestly. But a 2 by 2, I do those by hand just because it's quicker for me to multiply and subtract than it is to type it in. Y'all may be quicker at typing it in than I am. I'm just not real big on typing them in. For a 3 by 3, matrix. Let's say, we were asked to find the determinant of 6, 2, 4, 8, 9, 3, 1, 2, 0. I am not doing that by hand. I'm just going to type that thing into the calculator and tell it to find the determinant of it. Second matrix, edit. We'll go to matrix C, make it a 3 by 3. 6, 2, 4, 8, 9, 3, 1, 2, 0. And then I need to do matrix math, DET, of matrix C. Mine was in C. I get -2 is the answer. Which again, it's just a property of it. If the determinant is 0, it means something when you solve systems with determinants, but we're not solving systems with determinants. That can be done by hand. If you want to know how, shoot me an email and I'll link you to a video that I've done on how to do them by hand. Why you would need to know how to do them by hand, I can't place a reason on you for that, so I wouldn't worry about that at all. Okay. All right. So determinants. That's section 5.3. All right. Through the advancement of mathematics, they told us to skip section 5.4. So we're moving on to section. I said 5.5, but I actually want to jump over to 5.7 and come back to 5.5 and 5.6 and do some other things with matrices. All right, so 5.7, properties and operations with matrices. Since we're doing matrix stuff, let's go ahead and do some of these things. All right. Now, one of the things that they're going to ask you to do is, and I'm not, every time I've given the final for 110 or college algebra, they've always put a problem on there where they give you this matrix. Maybe it's 2, 4, 7, -5, 8, 3. And they say perform this row operation. Okay. So perform a certain row operation. They might say row 1 is equal to 2 times row 2 plus row 1. And that's how they would write it over here on the side. They'd say take row 1 and change it by doing this. Multiply row 2 by 2 and then add it back to row 1. So what you got to know is that row 1's the only one that's changing. It may say multiply row 2 by 2, but it doesn't mean you change row 2. It says row 1 is equal to something. That means row 1's the only guy that changes. That's what you've got to realize with this. So when I go to do this, I just copy row 2 down because I know it's not changing. Row 1 is the only person that's changing because it says row 1 equals. Whatever it says equals, that's the row that's changing. R1 is row 1, R2 is row 2.
So would you do 1.3, get that answer?
Well, I'm going to go from here and I'm going to say, okay, 2 times row 2 plus row 1. So it's each spot. So we look here, we got a row 2, -5. We'd say that times 2 is -10. Plus 2 would be -8. And that's what's in the first spot for row 1 is -8. And then we look at this one and it says 8. 8 times 2 from there. 8 times 2 is 16. 16 plus row 1, 4, is 20. So that's what goes there. And then 3 is in row 2. We double that. 6 plus row 1. 6 plus 7 would be 13. And that's the answer. No more complicated than that, really. They don't get too crazy. Even on like a 3 variable system or a 3 by 4 matrix. Maybe you got 6, 23, negative 21, 7, 3, 21, negative 27, 12. And the last row is negative 8, 10, 2, negative 13. And maybe they say perform this row operation. Row 3 is equal to 1/3 of row 2 plus row 3. Which row is changing? Row 3. That's the only one that changes. So that means I need to just go ahead and copy down which 2 rows. 1 and 2. I'm not changing those. I'm just doing some work on row 3, and we'll make it look different. So 1/3 times row 2, and then add it to row 3. So 1/3 times row 2, so times 3. 1/3 of 3 would be 1. 1 plus negative 8, negative 7. 1/3 times 21, 7, plus 10, 17. 1/3 times negative 27 plus 2. Good. 1/3 times 12 plus negative 13. Negative 9. You've performed that row operation. Not very difficult. If they ask you to do more than one row operation, do the first one, get its answer, and then do the second one on that answer. So you just do them in order of way they gave them to you. Okay? They don't get too crazy with these. It's very straightforward on the row operations. And again, I don't do those inside the calculator. It has the capability to do it, but it's pretty complicated in how to type it in. And it's less, I think, less confusing to just do it this way than it is to try to teach you to type it in the calculator. Yes, sir.
Okay, on me, I just want to make sure I see this right. When it says R3 equals, whatever, R3 is the row that's changing, right?
That's right. R3 is the only row that changes.
And it's basically saying 1/3 times the first value.
Yeah, each value in the second row. That's right.
And then you add whatever's on R3.
Mm-hmm. That's exactly right. It is exactly that. It seems too simple, but it is exactly that. All right, let's look at some operations with matrices. So the first operation is we always do the easy stuff first. Add or subtract. To add or subtract matrices, they must be the same size. Okay, they have to be the same size. So a 2 by 3 can add to a 2 by 3, but a 2 by 3 can't add to a 3 by 4. They have to be the exact same size to add or subtract them. Must be the same size. Okay. I don't know what letter are we on here. C? Is that right? Yeah, C. All right. So let's say we got a couple of easy ones. 5, negative 6, 8, 9, plus negative 4, 6, 8, negative 3. So what size is the first one? 2 by 2. Is the second one 2 by 2? So that means it's legal to add them. So we're going to add those two together. So you add the matching spots. So first top left plus top left.
Should be 1, 0, 16.
Good job. I know where you got those numbers. Anybody confused? 5 plus -4 is 1. -6 plus 6 is 0. 8 plus 8 is 16. 9 plus -3 is 6. Matching spots. That's why they got to be the same size. If they're not the same size, you can't have matching spots, right? So that's why they have to be the same size. You could. It makes things really, really complicated, though. Used to lay tile a lot back in the day. I was in college. Make pretty good money doing that. Every weekend I'd come home, he'd have a tile job for us to do. Mm-hmm.
He worked the last 2 or 3 years. He's made stuff. He's going off no scholarship to college.
Must be nice. Subtraction, same idea. Got to be the same size. Are these two the same size? Yes. First 3 by 2, 3 by 2. Corresponding spots. Subtraction. 8 minus 6. 2. -10 minus -4. 6. 6 minus 1. 5 minus 8. -3. -7 minus 5. -12. 18 minus 9. This can be done in the calculator if you want to. I usually don't, but you could. You just put the matrices in there, and then you tell your calculator matrix A plus matrix B or matrix A minus matrix B. You can do it that way with the calculator. We'll get to a little bit more complicated stuff in just a second, but the calculator is kind of handy to do. Yeah. All right, so adding, subtracting, very, very easy. Scalar multiplication, also very easy. Scalar multiplication, it's just think distributive property. Scalar multiplication is taking a number and multiplying an entire matrix by that number. It's like distributive property. So I'm distributing a 3 to every element of that matrix. So 3 times 6, 3 times -8, 3 times 10, 3 times 2/3, 3 times 4, 3 times -13. Everybody gets multiplied by that number that's in front. So that's 18, -24, 30, 2, 12, -39. That's scalar multiplication. Everybody inside gets multiplied by the number on the outside. It's like distributive property does. But it's called scalar multiplication because it's dealing with a matrix. Very, very easy idea. Okay. All right. The more difficult thing would be multiplying matrices. There's a couple things you need to know. It is not commutative. Commutative property in math means what?
Same size.
No. 2 times 3 is also equal to what? 3 times 2. You can change the order and it be the same answer. Numbers multiplication is commutative. Matrices, matrix A times matrix B may not equal matrix B times matrix A. They're not commutative. That means you can't change the order and it work the same. Okay, not commutative. Okay, so that's big. Now, columns in the left matrix must match rows in the right matrix. So if you're multiplying two matrices, a 2 by 3 times a 3 by 4, these two numbers have to match. When you look at the dimensions, the size, 2 by 3 times a 3 by 4 is legal because those two numbers in the middle match. If they're different, it cannot be done. It's an undefined operation. Okay. The neat thing about it is the resulting matrix will be this size, 2 by 4. The outside tells you how big the answer is. Inside's got to match. Outside tells you the size of the answer. Okay. This can be done by hand. It's not real easy to do by hand. It's a lot of operations. It's multiply, and then you got to add for every individual element. Each spot has to have, depending on the size of the matrix that you're doing, it has to have a couple of multiplications and then an addition. And then you go to the next spot, and it's got a couple of multiplications and an addition. And then you go to the next spot, and it's got the same things going on. And it adds up into the number of operations that you have to do. So multiplying matrices, I'm not expecting you to do this by hand. We're going to do it on the calculator and work it out. So let's put in a couple of matrices. Let's call this one matrix A, -3, 7, and 2. And let's call this one matrix B, 1, 0, -1, 2, 3, 1, 4, -1. I don't know what letter are we on here. F. Example F is find A times B. All right. What size is matrix A? 2 by 2. What size is matrix B? 2 by 4. Is a 2 by 2 times a 2 by 4 legal? Numbers in the middle match. What size is our answer going to be? 2 by 4. Okay. So A times B is going to be a 2 by 4 matrix. Draw myself something big enough to get a 2 by 4 in. Okay. So in my calculator, I'm going to enter matrix A into matrix A and matrix B into matrix B. Second matrix, edit A, it's a 2 by 2, 1, -3, 7, 2. Second matrix, matrix B, this one is a 2 by 4, 1, 0, -1, 2, 3, 1, 4, 1. So I've entered that in there, and now I just want to tell my calculator to multiply them together. So I'm going to go to second matrix, and I'm going to tell it matrix A times matrix B. That's the order that it asked me for, or that I asked you for, A times B. And there's our 2 by 4 matrix that we get back. -8, -3, -13, -1. 13, 2, 1, 16. Example G, find B times A. Matrix B is a 2 by 4. Matrix A is a 2 by 2. These two numbers in the middle don't match. So we say that's undefined. There's no solution, no answer to that. Undefined is how we say that. Well, not bad, not bad. All right, let's move on to something else called equal matrices. If two matrices are equal to each other, then that means their corresponding parts are equal to one another. So if I ask you to find x for this problem, what should x equal? Because that's the spot that matches up to where x is at. If I ask you to find y, y would equal 1, because that's the spot that 1 lines up to. If I ask you to find q, q is equal to 0. Find p, p is equal to -1. Corresponding parts are equal. Now, this is a very, very simplistic example. We're about to get to one that's not as simplistic. But the idea is that the corresponding parts go together for whatever variable you're looking for. So when we look at one like this, 7x3, 5, 10, y, plus another matrix, 8, -6, 10, 5, 16, 7. And then we have a third, and it's equal to this other matrix. 15, 10, 13, 0, 26, 14. And we want to find x. That's the first problem. What parts go with x? Yeah, x is right here. So -6 and 10 goes with that. So what we do is we set up an equation. Looking at the matrix on the left, if we're going to add those two matrices together, they're the same size. They're both 2 by 3s, so it's legal. X would add to what? -6, and that should equal 10. So we create this equation based on the matrix equation we have up here. And then we just solve that. X would be equal to 16. If we're asked to find y, what's the equation that we could set up for y? Good job. Subtract 7. Y is equal to 7. This is not like a system of equations like we were dealing with earlier. This is just a matrix setup where we have a couple matrices added together. They're equal to another matrix. And we just look for corresponding parts, the parts that go together. Okay. All right, so y, what we've got matching up here, y is right here. So there's the 7 that goes with it, and there's the 14 that goes with it. So it's y plus 7 is equal to 14.
Sorry, I couldn't see the Y.
Yeah, all right, that's okay. That's all right. And then if there's any other operation going on there, if there was like a scalar multiplication out in the front, you could go ahead and do that scalar multiplication with it as you set up your equation. Like if it was 2 in the front of that, you'd have 2y plus 7 is equal to 14 or something like that. You know, if there's a scalar multiplier out in front, you can follow order of operations with that and still be okay. All right. Okay, let's go to section 5.8. And it's another one of those graphing calculator sections where we're going to use the calculator to do the work for us. Inverse matrices. And I'll show you how these work. Inverse matrices are like, what's the inverse of 3? That would be the additive inverse. What about multiplication? One-third. 1/3 times 3 is 1. That's what happens here. Inverse matrices, the way they work is they cancel out a matrix. If it's an inverse and you multiply them together, they cancel each other out, is what happens. What we're going to use here, we're just going to use the calculator to help us find those inverses. You could do row operations to get you there, but it's not necessary for our purposes to do that. The row operations, tons of, depending on if you pick the right path, what's the easiest way to get there. If you don't pick the right path on the row operations, you could end up getting there, but it may take you 2 pieces of paper to get there. Where if you picked a different path, it may have taken you 3 steps. So that's where we kind of fall apart with the row operation. So I don't ask you to do that. So we're just going to find the inverse of matrix A. And this matrix A is a square matrix. It's 1, 0, 1, 2, negative 2. Well, it should be negative 2, negative 1, 3, 0, 0. And the way we do the notation for inverse is the way we did inverse functions. We just put a -1 exponent. That's the way we use that notation. So all we have to do here to get the inverse of a matrix is type that matrix into our calculator first, the original matrix. So second matrix, I'm going to use matrix A. I'm going to convert it to a 3 by 3. And I'm going to type in that matrix, 1, 0, 1, 2, negative 2, negative 1, 3, 0, 0. Oops, second. And then to get the calculator to do the inverse, all you have to do is go grab the matrix that you want the inverse of, get it to put that name there, and then there's a button right here on the left. If you press X to the -1, it puts the little -1 exponent there. It's on the left there. So you get your matrix typed in, and then get that inverse button and hit enter. And then I'm going to make it do it in fractions because we don't want decimals. So math, enter. We'll do another one. That's my inverse matrix. 0, 0, 1/3, -1/2, -1/2, 1/2, 1, 0, -1/3. 0, 0, 1/3, -1/2, -1/2, something, 1/2. That's -1/3, 0, 1. And that's the inverse matrix. We found the inverse matrix for a matrix of any kind. Okay, let's do another one. Let's do example B. Find the inverse of this matrix, and we'll do a 2 by 2. Let's do 2, -5, 7, 8. And to find the inverse, it's got to be a square matrix anyway. Just like find the determinant, it has to be square. It'll be same rows, same columns. Inverses have the same rule. So in my calculator, I'm going to type in that matrix. Unlike determinants, 2 by 2 inverses are not always easy to get. 2 negative 5 7. Quit, and then I'm getting the matrix that I used, and then hitting the inverse button, which is right underneath the math button right there, x to the negative 1. And that's ugly, but if I hit math, enter, it gets a little bit better. 8 over 51, 5 over 51, negative 7 over 51, 2 over 51. Oops. 8 over 51, 2 over 51. Negative 7. Whoop, that's 5 over 51. And that's the inverse of that matrix. I bet you the determinant's 51. 16 minus 35. Minus negative 35 is 51. Yeah. Those are interesting properties that happen there. All right. Where is that useful? It's useful in solving a system of equations. So use inverse matrices to solve a system. So maybe we have this system, 2x minus 3y equals 4. X plus 5y equals 2. All right. Letter we're on C. Now, we know our REF works to solve this system. That's how we would normally do this. The reason I want to show you this is because every semester they've always put a question on the final that says what inverse or what matrix should be multiplied to solve this system. And it's using this idea that you use an inverse matrix. So what we have to do is get the coefficient matrix. The coefficient matrix is just this stuff. So it's 2, negative 3, 1, 5. That's the coefficient matrix. Okay. The idea is that you find the inverse of that. Okay. We'll find A inverse. So in my calculator, I'm going to go over here and I'm going to go into matrix, edit, 2 by 2. I'm going to enter in this matrix. 2, negative 3, 1, 5. And I'm going to get the inverse of that. And I'm going to cheat a little bit here and go up here and grab that command and hit enter. And I'm going to hit math, enter, enter. And I get that matrix. Five over 13. What was it? 3 over 13. And then negative 1 over 13, 2 over 13. So maybe I can remember that. All right. So that's the inverse. To solve the system, you take A inverse times A, and this is really what you do, times the augmented part, which is 4, 2. That's how we're going to solve this. And that's going to get us X and Y. The solutions for X and Y. So in my calculator, I need to enter in that 4-2 matrix, that 2 rows by 1 column, a 2 by 1. And I need to enter it in somewhere besides A. So second matrix, over to edit, down to B. That's a 2 by 1. And it has 4 and 2 in it. That's coming from our system of equations up here that we started with. That it's equal to, each problem there is what this would be the augmented part if we did RREF. Okay. Now I'm going to use the inverse that I found already. So I'm on the regular calculator screen. This matrix right here is the inverse. So I'm going to grab it, or better yet, I'm going to grab that command, A inverse times that matrix B. So I'm going to grab matrix B, that 2 by 1. And there I get my X and my Y. 2, 0. X equals 2, Y equals 0, ordered pair 2, 0. Yes, I know, RREF, much, much easier and a lot more clean to do that. Big thing that I want you to catch out of this is just the fact that you use the inverse matrix. Know that if it asks you what matrix do I use to solve this, you use the inverse matrix. And that is that guy right there. There is a question on the final that asks that question. Which matrix would be used to solve this system of equations? It's the inverse of the coefficient matrix. The inverse of the coefficient matrix. And you find it. You actually have to do inverse with your calculator and find that which one would work. Okay. Again, RREF is the way you want to solve them. But because they put that theory question on that final, I want to give you one that works. All right, so on the last part here, I'm using this. This is that ugly matrix there with the fractions in it. That's A inverse. I'm multiplying it times this stuff, a matrix that has 4 and 2 in it. Just a 2 by 1 matrix. 2 rows, 1 column. What the equations were equal to. When I multiply that inverse times those two, it's going to give me my X and my Y. And that's what this was, is the X and the Y. So your inverse times what it's equal to gets you your variables in order alphabetically, X, Y. If there were 3 variables, it'd be X, Y, Z, that sort of way. Does that make better sense? I know it's not, again, RREF's the way you're going to do it most of the time, but there's this one question that always comes up on the final that I'm just saying, this is what it's asking for, and I want to put it out there for you to do.
So we only do that whenever they ask for what matrix is going to solve.
Yes. Yeah, I that definitely would not be the style that I would put out there. So I'm going to write up the practice problems for this week, and again, I'm going to do a Canvas quiz that's optional. It won't hurt you, but it could help you. Because remember, I'm dropping your lowest one, and this one could be higher than one of your others out of that thing. So this definitely a good opportunity to up some grades on those Canvas quizzes that we need. And that quiz will be available sometime tomorrow. We didn't have school today, so I didn't work today at home. Page 565. Just pick some of those problems. Now, here's what else I'm doing. Labs. The labs that go along with these, I'm handing to you tonight as the work that you need to do. If you see them, great. I'm awesome on both. Yes. All right, before you get out of here, let's make some notes on these labs as to how you want to solve them. Because the instructions say do one thing, but I expect you to do a different way. Okay, so on lab 22, the very first one, the first page says the instructions say solve each the following systems of linear equations using the substitution method. What method do I expect you to use? The calculator, the RREF. If you want to do substitution, more power to you. Go for it. Check them with RREF at least. Okay, solve those with the calculator. Okay, RREF. Page 2, flip that over. It says solve the following systems of linear equations using the elimination method. If you want to use elimination, more power to you. Go for it. I don't discourage you from doing that. That's a good method. But what do I expect you to do? RREF. Got that too with the calculator. It's so much easier, and it's going to get you the right answer. If you can type in the problem right, it'll get you the right answer. So RREF on that one. Page 3. Solve each of these systems using the intersect feature on your calculator. We didn't talk about that. We talked about what the picture would look like. Be sure to give exact values for your answers, not decimal approximations. That means fractions. If it's fractions, it's not perfect. What method am I expecting you to do? RREF. This is the same lab, page 3, number 7 and 8 there. Page 73 at the bottom is what it says. Got it? Okay. I'll give you a copy of the manual. Sometimes copy machines use correct. All right. RREF so far. Lab 23. Page 75 at the bottom. 3 variable system. It says use the elimination method. They didn't give you enough space to do that anyway, because it would take that much more. So what method am I expecting you to do? RREF. It carries on through number 4. Flip it over to the back side of that. Get to lab 24. This one says use Gauss-Jordan method, RREF in parentheses. That's the other name for that. To solve each of the following systems of equations, be sure to write down the augmented matrix, the final matrix, and the solution set. We're following the instructions, because that's exactly what we did. We didn't call it Gauss-Jordan, but Gauss-Jordan is what it's called. If you're on Jeopardy and that comes up, come up on Jeopardy, they don't ask me questions for a reason.
Okay, and the solution set is the what?
The order triple, like the parentheses X, Y, Z.
Okay.
All right. Now, that leads us to the last thing we got to cover before we get out of here. Okay. That got us all the matrix stuff. Now, the last thing we got to cover before we get out of here is the nonlinear systems and then the linear programming. So I want to go over that real quick before I know you thought, oh, we're done, we're going on. I want to get all that matrix stuff written down on those labs first, because that's the majority of the labs. Okay, we got one more, well, actually 2 more sections here that are fairly short on nonlinear systems, and then the inequalities is really short. So let's look at that really fast and see if we can get somewhere with that. So this is non-calculator stuff. So this is real math here. Nonlinear systems. Okay. Nonlinear systems of equations are going to be like this. X squared minus y equals 4. And then x plus y equals -2. Okay. All right. Now, we can tell that's nonlinear because that first equation has an exponent on the variable. That makes that not a straight line. So that's nonlinear. Now, this is where the substitution and elimination methods come back. This is where you would need to know them. Okay? Because when I'm going to solve this, I need to solve it using one of those methods to help me get an equation that can be solved. So I'm going to use the elimination method. Because remember, I said it's my favorite method. It works really good on this one because look what we have here with the y's. Well, it would be, I've got the y's, negative y plus positive y is going to cancel out. On the left over here, this is x squared and this is x. Are those like terms? No, one's x squared and one's plain x. They're not like terms. So it ends up being x squared plus x. And then on the other side of the equal sign, we got 4 plus negative 2 is 2. We get a quadratic equation to solve. How do we solve quadratics? Okay, what's got to happen first then? It's got to be equal to what? 0. So I'm going to move the 2. So that's x squared plus x minus 2 equals 0. And you're right, quadratic formula would be a great way to solve this. So 1 squared minus 4 times 1 times negative 2 over 2 times 1. And I work that out, and I get negative 1 plus or minus be 1 plus 8, which is 9, square root of 9 over 2. What's the square root of 9? 3. So I end up with negative 1 plus 3 over 2, negative 1 minus 3 over 2. That'd be 1. That'd be negative 2. I get 2 answers for x. So that means I better get how many answers for y? 2 of them. Okay? So we're going to get those by just going back into one of our problems here. I'm going to go back into the easiest one. That second one is a lot easier because it doesn't have the x squared in it, right? That makes the problem easier when it doesn't have an exponent. So I'm going to go 1 plus y equals negative 2. That's going back into x plus y equals negative 2. So subtract 1, y is equal to negative 3. So the ordered pair would be 1, negative 3. And if I go back into the same problem with the negative 2 plus y equals negative 2. Add 2. Y is equal to 0. The ordered pair would be negative 2, 0. Those are my 2 answers for this nonlinear system. Which is kind of ugly, but not impossible. So you're using one x and get an ordered pair that goes with it. Use the other x, get the ordered pair that goes with it. If we had a third answer, we'd use that x and get the third ordered pair that goes with it. Depending on how many answers you find is how many ordered pairs you'll have at the end. Okay? Let's look at example B. X squared plus y squared is equal to 4. 2x squared minus y squared is equal to 8. Man, all of these are squareds. What cancels out? Yeah. We got a plus y squared and a minus y squared. So they would eliminate each other if I added these two equations together. And then what's on the left side? X squared, 1x squared plus 2x squared. Are they like terms? They're both x squareds, aren't they? So what's 1x squared and 2x squared is 3x squared. And 4 plus 8 would be 12. Hey, that's a pretty easy one to solve. I just divide by 3 and I get x squared is equal to 4. And I take the square root of both sides, right? Plus or minus the square root of 4 is 2. So plus or minus 2. I got 2 answers. I got x equals 2 and x equals negative 2. Take those and plug them back into one of my problems. Pick one. They both have squareds on everything, so it doesn't matter. I'm going to go to the easiest one the top one, x squared plus y squared equals 4. And I'm going to go, well, what happens when x is equal to positive 2? So that'd be 2 squared plus y squared is equal to 4. And that's 4 plus y squared is equal to 4. Subtract 4. Y squared is equal to 0, so y would be 0. So the ordered pair would be 2, 0. Then I would do the same thing. I'm going back into x squared plus y squared equals 4 when x is negative 2. Negative 2 squared plus y squared is equal to 4. Looks like it's going to work out the same, which is okay. Y is equal to 0. So we end up with this ordered pair negative 2, 0 and positive 2, 0. Doing elimination and then getting like terms together, solving for a variable.
Since we're only covering, more or less, not, 4 weeks worth of material, that's just gonna be shorter, or it's the same about
It'll cover all the material. I don't know how many questions will be on it. But it'll be, the blackboard, the Canvas quiz will be similar to what the test will be like. Because it'll have everything on it too. So that's another incentive to do that, regardless whether it, works for your grade or not. All right, let's do this one. All right, here's our equation. X squared plus y squared equals 16. The second equation has absolute value of x plus y equals 4. All right. Now, this one's weird because you don't have things canceling each other out. We don't have y squareds that cancel each other. We have a plain y, and then we have x squareds and y squareds. And we got an absolute value of x, which is the weird part. So with the absolute value of x being the weird part, that means that triggers me. I'm just trying to get you going through my thinking process here. If I see that, I'm going to try to get that by itself. So if I subtract y, that gets the absolute value of x is equal to negative y plus 4. What's absolute value always give you? Positive answers. What's x squared always give you? So that would mean those are very similar things, right? Not exactly equal, but they're very similar, right? I could take this and substitute it back in for x there. And get a problem that only has y's in it now. Now, when I square negative y plus 4, I'm going to get y squared minus 8y plus 16 plus y squared is equal to 16. So that's going to be 2y squared minus 8y plus 16 is equal to 16. It's got a y squared in it, so what's it got to be equal to? 0. So I move the 16 over. Turns out that cancels out to get me 2y squared minus 8y equal to 0. I could do quadratic formula. A is 2, B is negative 8, C is 0. Or I could do just factoring. And the factoring is quicker. It's 2y, and then this would be y minus 4. You get 2y is equal to 0, y minus 4 is equal to 0. So you get y is equal to 0 as an answer, and y is equal to 4 as an answer. But we got to find the x's that go with that. So when y is equal to 0, this is what happens. If I go back into x squared plus y squared equals 16, I'm shying away from the absolute value problem because that's kind of weird. Squaring something's not real weird, but absolute value, when you start solving in an absolute value equation, that gets a little weird. So if I plug in a 0 for y, I get x squared plus 0 squared. What's 0 squared? So that'd just be x squared equals 16, right? Oh man, that's a pretty easy one to solve, right? Take the square roots. Plus or minus 4. So we get ordered pairs 4, 0, and negative 4, 0 out of that. What happens when y is equal to 4? If I plug that into that same problem, I get x squared plus 16 equals 16. Subtract 16. X squared is equal to 0. The square root of 0 is 0. And the other ordered pair would be 0, 4. We found all 3 ordered pairs out of that. Okay. Now, nonlinear systems is what that's dealing with. Okay. When you look at lab 25 that you've got in your hand, those are the methods that you're probably going to want to use to solve those. Number 1, you got some elimination happening. Number 2, I would solve the first one for y and then plug in, substitute. Number 3, I would probably, let's just go ahead and eliminate number 3. And number 5. I'm going to mark that on mine too. Eliminate number 3 and number 5. Omit those. So you're only doing 1, 2, and 4 on lab 25. All right, lab 26 is really all that I'm after from the last section on system of inequalities. Systems of inequalities. / linear programming. All right, so what you have with the linear programming is you have a set of inequalities. Like when you look at lab 26, you see these boxes that are drawn and shaded in. Those boxes were created from a set of inequalities. Boxes came from a set of inequalities. On the test and on the final, they give you that box already drawn. You don't have to draw the inequalities and graph them. Okay, they give you that box already drawn. Okay, the boxes come from the set of inequalities. You need the corners. Ordered pairs. Another word for those are vertices. A geometry term. Corners of a polygon are called vertices. That's what you need. X ordered pairs, X comma Y. You have what's called an objective function. Plug in the ordered pairs. And find the maximum and minimum. Maximum, when you plug in the ordered pairs, you're looking for the biggest number. Minimum, you're looking for the smallest number. It's asking you to do both. So if you look at Lab 26, it's got a polygon already drawn. It's got the ordered pairs marked. You don't have the numbers. All you got to do is get the X and Y coordinates for that dot. Like, so that bottom left one would be 4, 2. And you would plug that in to the objective equation or objective function that they have written there for number 1. X would be 4, Y would be 2. And you get that number. And then you would do the same thing for the next ordered pair, 7, 4. You'd plug that into the objective function, get that answer. You would do that again for the next ordered pair, 7, 9. You'd work that out. You'd get a number. And then you would do the fourth ordered pair, 12, 11. 12 for X, 11 for Y. You'd work that out and get a number. Then you just pick the biggest one as your max. You circle it and write max. The smallest, circle it and write minimum. That is what we're doing on that linear programming stuff. When you go to number 2, it just same picture, same ordered pairs, different objective function. So you plug the same ordered pairs into a different objective function, should have a different maximum and minimum from an ordered pair. Okay. On number 3 and 4, it's a new picture, new equations. Get the ordered pairs that are the corners of the polygon, and then plug them into the objective function for X and Y. Work it out. Biggest one is your max, smallest one's your min. The others don't matter. That's really all there is to that. I'm not smoking mirrors or anything. It really is that. That's the linear programming side of things. Systems of inequalities, it's just graphing the same lines and shading those. We did that in Math 100. That's something you should be able to do, is graph some regular inequalities on the same coordinate plane. Again, going to have the box, you just got to get the ordered pairs out of it on the final, on the quiz, on the test, out of that thing. So that's it for tonight, actually. So things going on this week. You got the labs that you're doing. This is, you're doing these. The Canvas quiz will be out. I'll put it online tomorrow, barring any crazy things happening. I'll send out a message reminding you of that and what the circumstances are with it. Test next week. We will come in at 5:45 next week, and we'll have a short Q&A question answer on these labs. If you got some questions, we're not going to spend a ton of time on it. I would like to have the test started by 6:30 at the latest. We'll take questions until you're done, and at 6:30 or before we'll start the test, and then you'll get your practice final, and that'll be it. We've got 3 more class meetings. It's crazy. It's almost gone. So that's the plan for the week. If you got any questions, email me. You still got that option. Always a good option to have. Other than that, I'm done with you. You guys have a good week. Happy Easter to you. Be safe.